Our goal now is to approximate the natural log function. In particular, let's approximate ln of 1.5. By the definition of the logarithm as the integral from 1 to 1.5 of, well, we wrote 1 over t dt before, but now I'm going to go to x. You know, the variable name is irrelevant. I'm going to go ahead and use x here. This is going to be the function f of x that I'm trying to numerically integrate. I suggested you watch the video that I made 3 years ago, talking about numerical integration as I would teach it to a calculus class. That is all stuff you should feel comfortable with, including a fair amount of Mathematica. We will use Mathematica today as well, but I want to focus on the more traditional way to approach numerical integration that is found in the textbook in sections 4.3 and 4.4, though I only suggested to read 4.3 last time. Let's think about this real simplistically, you might say. We are trying to approximate an area under the graph of 1 over x, making it fairly big this time. There's x equals 1. The output of f of x equals 1 over x at 1 is also 1. This integral is going to give us the area under this curve from 1 to 1.5, which is 3/2. The output at 3/2 happens to be 2/3, 0.6 repeating. I'm really trying to estimate this area, to estimate ln of 1.5. Okay. Again, let's approach this pretty simplistically. Initially here, in terms of the left and right hand rules, with n equal to 1, we'll only use just one subinterval. Isn't that fun? Right? Won't get the greatest approximation, but it will be nice and simple. If we use, for this one interval, we could use a left-hand sum to approximate the area under the curve. What does a left-hand sum give? It gives you the area of this rectangle right here, which you can see is actually pretty easy to calculate in your mind. Base times height is 0.5 times 1 is 0.5. That area will be 0.5. So that would be a left-hand sum approximation to the integral, an approximation to the natural log of 1.5 with one subinterval. We could also do a right-hand sum approximation by finding the area of this rectangle right there. And you can see base times height there would be 1/2 times 2/3, 1/3. That area is going to be 1/2 times 2/3, 1/3, 0.3 repeating. The true area we're after, which represents the true value of the natural log of 1.5, is somewhere between 1/3 and 0.5. Maybe about halfway between them, about. Not exactly, because of the curvature. If the graph were a straight line, it would be halfway between them. Thinking in terms of what we've learned in terms of interpolation back in chapter 3, what we're really doing here is we're using, you might call them degree 0 approximations to the function. One, I'm going to go ahead and call x0. And 1.5, I'm going to go ahead and call x1. We could also call this a and this b. Right, in calculus, typically the left endpoint's called a and the right endpoint's called b. But here in numerical analysis, we've also been using subscript notation. x0 and x1 are nodes. Degree 0 approximations, whether you think of them as Taylor polynomials or Lagrange polynomials, are constant functions. This one's f of x0, and this one's f of x1. So what we have here is we can write the integral from 1 to 1.5 of function f of x, where f of x we are taking to be 1 over x. we could write it's approximately f of x0 times delta x. This 1/2 you could think of as a delta x if you like, or to be consistent with our book's notation, an h. This is f of x0 times h, which is f of 1 times 0.5. This would be a left-hand approximation. Why left-hand? Because I'm using the left endpoint of the interval, x0, to approximate the height of the graph, effectively. F of x0 is 1. The value of the red graph, 1/x, at the left endpoint of the interval. I could also say the integral from 1 to 1.5 of f of x is approximately f of x1 times h, which in this case is f of 1.5 times 0.5. You could call that a right-hand approximation. Okay, it's pretty simple. What I'm about to do is a little harder. In this class, being a numerical analysis class, we're interested in analyzing errors, right? That's our big theme. It's not something we've done every day. We've also learned numerical methods for the pedagogical purpose of also thinking about numerical analysis, of also thinking about errors. I now want to think about numerical errors. I want to do numerical analysis now. How? I'm going to write down what's effectively Taylor's theorem, or the Lagrange interpolation theorem, in the case of one node, say x0. I'm going to go ahead and use x0, with an error term, with a xi involved. Okay? I can write by Taylor's theorem for example, that f of x, which yes, is still the 1/x function, but I'm going to write down the general formula here, is f of x0 plus, well, that's the constant approximation. That's the degree 0 approximation. Plus the error term. What's the error term? The error term is going to involve the derivative. It's going to be f prime of c of x divided by 1 factorial times x minus x0 to the first power. This is a degree 0 approximation, a constant approximation. And this is the error term. It's a very crude approximation, right? A constant. Where c of x is some number between x and x0. By the way, I think I mentioned this before, but this is actually equivalent to the statement of the mean value theorem. This equation here, since 1 factorial is 1 and something to the first power is itself, this is equivalent to saying if you subtract f of x0 from both sides and then divide both sides by x minus x0, it's equivalent to saying f prime of c of x equals f of x minus f of x0 divided by x minus x0. This is really the mean value theorem. The statement of the mean value theorem, x is some fixed number. Maybe you call it b or something. And you're saying there's some number often called c between x0 and b such that f prime of c equals this fraction. The slope of the tangent is the slope of the secant line. Here I'm using an x instead. And the x could be any number, say bigger than x0. So the c depends on x. You see how these equations are equivalent? What are we interested in doing now? We're interested in coming up with an error term for numerical integration. That's why we're doing this. We're trying to do numerical analysis. We're trying to understand You know, we can do these approximations, but how good are they? What's the error? So to get the error, what we're going to do is we're going to take this equation and integrate both sides. From a to b, or if you prefer, from x0 to x1. Which is the same as the integral from a to b, because a equals x0 and b equals x1. These things are equal. I don't know what c of x is, but that's okay. So integrating the left-hand side is the same as integrating the right-hand side. And the right-hand side is a sum, so I could write it as the sum of two integrals, like this. So I'm just integrating both sides from x0 to x1. Again, my goal, keep in mind your goal, my goal is to approximate this integral here. Effectively, this is going to be your approximation, and this is going to be your error term. Hey, this integral is easy because guess what? X0 is a constant. This integral is f of x0 times x1 minus x0. Right? That makes sense? You could bring the constant f of x0 in front of the integral. You'd really be integrating the constant function 1 then. From x0 to x1, you're going to get x when you integrate. And you plug in the top limit of integration and subtract what you get when you plug in the bottom limit. Geometrically, you're just finding the area under this line here, base times height, area of a rectangle. That's what we just did there. The base is x1 minus x0. The height is f of x0. We could also call this h, or delta x if we like. What do I do about that integral, though? It looks really hard, especially since I don't know what c of x is. Well, it turns out there's another theorem that allows us to do something else with this to make it easier to evaluate. It's called the mean value theorem for integrals. Is it in the book? It actually is. I should have had you read it. Going back to the very first section, that section we keep going back to once in a while, section 1.1 with all the theory in it. There's the most general form, which we will use today, actually. But here's a more particular form that we're about to use. It's described as the weighted mean value theorem for integrals. Suppose f is a continuous function, that the Riemann integral of g exists, though g may not be continuous, but g does not change sign on the interval. Then there exists some number c between a and b where this integral equals this constant times that integral, f of c times the integral of g. It's kind of what intuitively, we're not going to prove this, but intuitively, it's kind of like you're approximating f of x with f of c, the constant f of c, over the interval. And because f of c is a constant, it's like you're factoring it out. And you have to prove that you can do that. But that's kind of the intuition. When the g of x happens to equal the simple function 1, this integral on the right is the integral of 1 from b to a, which is just b minus a. And so the integral of f can be written as f of c times b minus a. Catch what I just said? Say it again. You're listening? The integral of f, when g of x is the constant function 1, is f of c times the integral of 1. And again, the integral of 1 is b minus a. That's effectively what I just used. Or what I'm about to use, sorry. This f prime of c of x is like the f function in that theorem we were just looking at. And this function is like the function g of x. So there's some number c between x0 and x1 where this is true. Should I use a C? I could, but you know, I like C so much, I'm going to use a C again. But now this is a C that doesn't depend on X anymore. No dependence on X. Though it does depend on the integral, it really depends on X0 and X1. Times the integral from X0 to X1 of G of X. G of X is X minus X0. And guess what? That is an integral. Right here. That's definitely doable. Right? Integrating a linear function of X. Definitely doable. Let's do it. Therefore, the integral, again, keep in mind what our goal is. Our goal is to represent this integral. It's f of x0 times h. I'll go ahead and use h here now. Plus f prime of c. Let's do that integral. Yes, I can do it piece by piece. It's actually a little bit more convenient, you might say, to integrate it as a whole. X minus x0 quantity squared over 2. Evaluated from x0 to x1. It's just a little bit more convenient to write the answer that way, because when we now evaluate this from x0 to x1, when we plug in x0, we get 0. And what do you get when you plug in x1? You get x1 minus x0 squared over 2. In other words, h squared over 2. Like that. And there's the form of your error term. Kind of the simplest form of your error term. So let's test this. Now with technology, let's get the exact value of the integral in a few different ways. Well, one with the calculator. Well, calculator is just going to approximate it. You know, in a calculator, if you're going to do numerical integration of 1 over x, you'd want to type the function in 1 over x. For your window, go 1 to 1.5. Maybe I'll keep the y min and y max as you see them here. Oh, no, maybe I should. Let's go 0 to 1. And let's make the y scale be 1/3, actually. Graph it. There it is. Go to the calculate menu. Go to integral. Lower limit is 1. Upper limit is 1.5. The approximation is about 0.4054651. That's the calculator's approximation. That's supposedly good to that many decimal places, exactly right to that many decimal places. Let's confirm it with Mathematica. If you type a decimal in there, it's going to give you an approximation, not an exact value. I should have warmed up the kernel ahead of time. There we go, 0.405465. 0.405465, yes, matching the calculator. This is supposed to be the natural logarithm of 1.5. LOG means natural logarithm in Mathematica. Same number. What does the left-hand approximation give? It gives f of 1 times 0.5, which is 0.5. What's the error? Remember, as always, the error is the actual value minus the approximate value. So in this case, the error is negative 0.0945. How does that jive with the error term that we got here? There's some number c between 1 and 1.5 where this equals what we got for the error, the negative 0.09. Do we need to find c? No, all we really need to do to think about errors here is think about what we typically do is think about an upper bound for this. Get an upper bound for the absolute error. The error is going to equal f prime of c over 2 times h squared for some c between 1 and 1.5, and the absolute error will equal that. And this will be less than or equal to the absolute value of f prime of c over 2 times the absolute value of h squared. H is a positive number, so I don't need absolute value signs. I'm squaring it anyway. If I can find an upper bound for the derivative of the function we're integrating, 1 over x, on this interval, then I can get an upper bound here. Again, f of x is 1 over x, which is x to the negative 1. So f prime of x is negative x to the negative 2, negative 1 over x squared. The absolute value of that gets rid of the negative sign. And on the interval from 1 to 1.5, this is maximized when x is 1. This is less than or equal to 1 over 1 squared, or 1, on the interval from 1 to 1.5. I can use this as an upper bound that you might call capital M for the derivative on the interval from 1 to 1.5. And I can go ahead and go up here and replace that absolute value with 1 and say I have a less than or equal to. So I get 1/2 times h squared. What is h for our problem? H is 1/2. So essentially, this derivation guarantees our error is less than 1/8 or 0.125 in absolute value, which it certainly is, because our error was negative 0.09. Its absolute value was positive 0.09. And it's going to work. This kind of thing is going to work over different intervals too. We did it on the interval from 1 to 1.5. Let's keep the bottom limit of integration 1. If we did it on some other interval, like 1 to 1.1, our left-hand approximation to the integral on the interval from 1 to 1.1, tracking with me here, it's going to be f of 1 times 0.1. 0.1. That would be the left-hand approximation area of a skinny rectangle, approximating the area under the 1 over x graph from 1 to 1.1. That's supposed to be an approximation for log of 1.1. What's the error in this case? Actual value minus approximate value. The error is about negative 0.0047. And what is our error? Instead of 1/2 times 1/2 squared, it would be 1/2 times 0.1 squared. H is now 0.1. Not 1/2. So when I evaluate this, I should get something bigger than the absolute value of the error that we got. Yes, it is bigger. By just a little bit. So you can see it's indicating as the h gets smaller, it seems like it's going to get a better and better approximation. You can do something similar with a right-hand sum. I won't take the time to do so. And you can get fancier and do similar things with the trapezoid rule, the midpoint rule, and Simpson's rule. But the algebra gets kind of nasty. So what should we do? We should study it and maybe use Mathematica to confirm it, but not worry about doing all the details by hand. So let's now study the textbook. The easiest one in the textbook is the first couple pages. We're going to study the derivation of the trapezoid rule. We will use Mathematica to help us believe what we see without verifying all the details by hand. Again, we're trying to look at the derivation here of the trapezoidal rule. The initial discussion is more general than on the first page or so than what you get on the next page or so. We are using Lagrange interpolating polynomials, which is different than the way we teach this in calculus. The purpose, though, is to get at the error term. Whereas in calculus, you're just told what the answer is. We want to see what the answer is, and we want to believe it. So we need to study this. We've got our nodes, x0 through xn. And this thing, that's the Lagrange interpolating polynomial. That's a linear combination of those L functions. Are you comfortable imagining what those L functions are in your mind? Right? Things like x minus x0 times x minus x1, blah, blah, blah on the top and the bottom. You replace all the x's with whatever node you're at. And those are designed to equal 1 at whatever node you're at, like node I, and 0 at the other nodes, and you multiply by the function values at the nodes, a linear combination of those Lagrange polynomials. That's supposed to be an approximation to f of x. Now, effectively, we're integrating both sides, including the error term. So the integral of f of x is the integral of the Lagrange approximating polynomial plus the integral of the error term. Yikes, look at that error term. We've seen this before. It should have a familiar field. Don't worry about the product for the moment. Focus on that. That's the n plus first derivative of f evaluated at some number c of x divided by n plus 1 factorial. With Taylor polynomials, we multiply that by x minus x0 to the n plus 1 power. With Lagrange interpolating polynomials, you multiply by x minus x0 times x minus x1 times x minus x2 times x minus x3 through x minus xn. There are n plus 1 factors there. They're using product notation for convenience. They're saying this integral equals that. How'd they get that? Well, effectively, they're integrating a sum. The integral sign can be brought inside the summation effectively, and these a's are effectively the integrals of the l's. Got the f of xi there, just like you have an f of xi there. The ai's are the integrals of the li's, and if you look at the next page, you'll see that. ai is the integral of li. Plus, what happened with the error term? Well, you factor out the constant 1 over n plus 1 factorial, but you still got to integrate this crazy thing where you don't even know what c of x is. But maybe, just like we did 15 minutes ago, maybe we can replace c of x with some fixed number c and factor it out of the integral. Yeah, that's what's going to happen. We have to use that weighted mean value theorem in its more general form, actually. That's what comes pretty soon here. So there's your approximation to the integral, where those a's are those integrals. And there's your error term. What's the goal now? The goal now is to think about this. This is a very general derivation. The goal is to think about this in special cases, simpler cases. Oh, how about think about this with just 3 nodes? x0, x1, and x2, or even 2 nodes, excuse me. x0 and x1. What we did 15, 20 minutes ago was think about it for 1 node, x0, using the Taylor polynomial at x0. Well, we're going to up the number of nodes to 2, x0 and x1. H is the distance between them. We're going to use both of these, not just the left or right endpoint here. What is the p of x, p function here? It's this. This is the Lagrange interpolating polynomial. Notice this term equals 0 when x equals x1, and f of x0 when x equals x0. And this term equals 0 when x equals x0. and f of x1 when x equals x1. It's a linear function. We're using a straight line between the endpoints on the graph to try to approximate the area of the curve. We're using a trapezoid. For our example, again, f of x equals 1 over x, and say still x0 is 1 and x1 is 1.5. What we're about to do is estimate the area under the curve here. Instead of using a function that's constant, using a linear function that's not constant. Using this function and the area of that trapezoid approximating the area under the curve. That's why it's called the trapezoid rule, or as the book labels it, the trapezoidal rule. They call it trapezoidal. I just say trapezoid. The trapezoidal rule. So this linear function right there is what you see right here. We could replace x0 with 1 and x1 with 1.5. We could replace f of x0 with 1 and f of x1 with 2/3 to figure out exactly what this is. But they're trying to do a general derivation. So just like before, the integral of the function we're after, in this case 1 over x, is the integral of the Lagrange interpolating polynomial, this linear function, plus the integral of the error term. Now, what do? Here's where they use the weighted mean value theorem. Effectively, it's like you're pulling f double prime in this case. It's f double prime because we're using a linear approximation, first degree, so the error term has to be a second degree, effectively, involving a second derivative of f at some unknown c of x. But effectively, we're going to pull this out. Why can we do this? Well, it's because the g of x function, x minus x0 times x minus x1, does not change sign in the interval. In fact, if you think about it, it's negative. And if you go once again back to that weighted mean value theorem in the very first section of the book, right here again, we're effectively using this equation where the f now is going to be f double prime of c of x. And the g is going to be x minus x0 times x minus x1. G does not change sign on the interval as part of the hypothesis here. The f in this theorem is, the role is going to be played by f double prime of c of x. This thing. And I guess with the 1/2 as well. So effectively, we now pull that thing out of the integral sign, and now they're just calling it c instead of c of x. It's a fixed constant between x0 and x1 instead of a function that depends on x. Probably would have been better to use a different letter there, like a c or something. Times the integral of that quadratic. It's a quadratic. The integral is fairly easy to do. Now the book goes ahead and does it and gets this, but realize they're not showing you many details. And in fact, I tried some of these details on my own this morning, and it was not pleasant. So then I tried it with Mathematica, and of course, Mathematica, once you know what to do at least, it's nice. Let's go ahead and do that, actually. Let's confirm that integral with Mathematica here. How? Instead of typing an x1 for the upper limit of the integral, I'm going to type x0 plus h. You can see the final answer involves an h, where h is x1 minus x0. But you can also see the final answer doesn't involve x0, so I'm ultimately going to have to get rid of the x0 somehow. What am I integrating? I'm integrating this product, x minus x0 times x minus x1, where x1 I'll type in x0 plus h. Let's see what this produces. Hey, evidently a bunch of stuff cancels involving x0. I didn't even have to use the simplify function. It simplified it automatically. That's where the negative h cubed over 6 comes from. Again, doing that by hand. I started to try this by hand, and I got to a point where like, I don't feel like doing it anymore. It was not pleasant. But evidently it does simplify to negative h cubed over 6. Which then now, after you multiply by 1/2, right, here, and don't forget about the f double prime of c, becomes a negative h cubed over 12 times f double prime of c. I guess I have that there too. There's your error term. And another thing that gets done here is to integrate this linear function, and you can verify with some work, some nasty algebra, that simplifies to this. So there's your approximation. There's your error term. And this approximation can be simplified because you can replace x1 minus x0 with h. To get your final result, the integral is approximately h over 2 times f of x0 plus f of x1 minus h cubed over 12 times f double prime of c, where c is some unknown number between x0 or a and b. A is x0 and b is x1. Another way to think about that formula is to realize that the approximation could also be written in this way. Okay, on the right side, I'm going to go ahead and use an a and a b. I could have used an x0 and an x1. They're the same thing here. You can think of it that way. And this can be interpreted as the area of a trapezoid if your function f has positive values. There's your average height of the trapezoid. There's your base. The trapezoid being this thing in red that I drew before. The area of such a trapezoid can be thought of as the average of the two heights times the base. The error term is this. It is a negative error term, or it has a negative sign, I should say, meaning that, for example, if your function has a second derivative that's positive, the error is going to be negative. Does that make sense? Hey, our example has a second derivative that's positive, concave up. So the error is going to be negative. Does that make sense? Error is actual value minus approximate value. The actual value is the area under the green curve. You can see visually is smaller than the approximate value, which is the shaded red area. Actual minus approximate is going to be negative. And I could also think about bounding the error. The absolute error is going to be the absolute value of negative h cubed over 12 times f double prime of c will be less than or equal to the absolute value of f double prime of c divided by 12 times h cubed. Is that going to happen? When we check this numerically, what is the trapezoid approximation in this case? It's f of 1 plus f of 1.5 divided by 2 times h. This should be close to the natural log of 1.5 here. I'm approximating the integral. I'm using the trapezoid rule right now. 0.416. Remember, the actual value is log of 1.5. The error then is that negative 0.01 approximately. What's this? Well, f prime of x was negative x to the negative 2. Therefore, f double prime of x is positive 2x to the negative 3, positive 2 over x cubed. On the interval from 1 to 1.5, that is bounded above by 2 over 1 cubed. It's biggest when x is 1. F double prime of x is less than or equal to 2 over 1 cubed, 2, on the interval from 1 to 1.5. So I can therefore say the error is less than or equal to 2/12 times 0.5 cubed, 1/6 times 0.5 cubed is going to be 1/8. 1/48 is going to be an upper bound for the absolute error. Yes, the absolute value of the actual error is definitely less than 0.02. Simpson's rule and the midpoint rule are the rules we haven't talked about yet. In the video I want you to watch, I do the midpoint rule before Simpson's rule, but today in class with our last 11 minutes, let's do Simpson's rule before the midpoint rule. We probably won't have time for the midpoint rule, in fact. What's Simpson's rule? For an integral of your function from a node x0 to another node x2, with a third node x1 between x0 and x2, and h being the distance between x0 and x1 and also between x1 and x2, Simpson's rule says this integral is approximated by this expression and then that error term, where that's a fourth derivative. The derivation of this is, as you might guess, even less pleasant. But you could trudge your way through it and maybe use Mathematica to do some algebra for you to confirm things. It's kind of an odd summation here. In the other video, I described Simpson's rule as a weighted average of the midpoint rule and the trapezoidal rule. Whereas since the midpoint rule, if you watch the other video, as you should, turns out to be twice as good as the trapezoidal rule, it gets twice the weight. This is something different, but it's equivalent, it turns out. So let's first use it to approximate natural log of 1.5 again. Let's see. So I'm about to use Simpson's rule. If I'm going to do that, though, I need 3 nodes instead of 2. I need a middle node between 1 and 1.5. I need 1.25. And the h is now 0.25 instead of 0.5. Simpson's rule in this context says the integral from 1 to 1.5 of f of x, I'm going from memory here, is h over 3 times f of x0 plus 4 times f of x1 plus f of x2. Kind of a strange thing. Let's just see that it gives a good approximation. H is 0.25. This is f of 1 plus 4 times f of 1.25 plus f of 1.5. F of 1 is 1. F of 1.5 we've seen as 2/3. F of 1.25, since 1.25 is 5/4, this is 4/5. 0.8, this is 0.6 repeating. Let's use the calculator to finish this. I'm going to go ahead and just add the numbers inside the parentheses here. 1 plus 0.8. 1 plus 4 times 0.8. I almost forgot to multiply by 4. Plus 0.6 repeating. This is 4 times 0.8 is 3.2 right there. When you add those, you get 4.86 repeating times 0.25 divide by 3 gives, it appears, 0.405 repeating as our approximation to log of 1.5, because it's our approximation to the integral. Again, log of 1.5 is what? 0.405465. Yeah, this is getting really close. Log of 1.5 minus 0.40555555. Maybe put a 6 on the end for good measure. Yes, the error is very small using Simpson's rule with just 3 nodes. Look at that error. Very small. This is a very good approximation. And just like before, since the error term is this thing, we could bound the error in absolute value by finding the fourth derivative, finding what it's bounded by on the interval from 1 to 1.5. It would be maximized by, or at least in absolute value, by the value at 1. Let's see, can I do the fourth derivative in my head? The second derivative was 2x to the negative 3. Third derivative would be negative 6x to the negative 4. Fourth derivative is like 24x to the negative 5. And would be bounded above by 24. So this could be replaced by 24. H is still 0.5. Let's go ahead and do this here. 0.5 to the 5th power. What did I say the fourth derivative was bounded by? 24 times 24 divided by 90 of all things. The error is bounded above in absolute value by that, which definitely ours was. Final thing I want to show you today. I was hoping to get to section 4.4, but it looks like we don't have time. No. What if you want to use more nodes to get better approximations? That's what 4.4 is about. We will do that a little bit on Thursday, as well as start talking about differential equations. But for our last 5 minutes, I want to give you a little feel for, shouldn't close the book, give you a little feel for where that comes from. What we're really doing is we're using 3 nodes, x0 equals a, x2 equals b, and x1 is halfway between them. H is half the distance between a and b. And we're using a quadratic Lagrange interpolating polynomial and integrating that to approximate it. With the left and right hand rules, we use a 0-degree polynomial, constant function. With trapezoid rule, we use the linear approximation, straight line. With Simpson's rule, you use quadratic. So to finish off class, what I'd like to do is use Mathematica a little bit and see if we can verify that formula. If you try to do this by hand, it's not so pleasant. Effectively, we're integrating. Okay, let's do it this way. We're integrating the Lagrange interpolating polynomial. With 3 nodes. First node being x0. Function value, let's call it y0 for simplicity. That's f of x0. Second node, x1, call the y value y1. Third node, x2, call the y value y2. It's going to be a quadratic function of x. There it is. Wow. Can it be simplified? Yeah, sure. Well, maybe not much. Maybe we want to expand first. Okay, well, maybe that's not much simpler. integrate that from x0 to, okay, oh, so here, maybe I should do something else here. Let's replace x1 with x0 plus h and x2 with x0 plus 2h. Let's try it that way. Hey, that's a little nicer looking. It's a quadratic in x. Notice there's your x minus x0 quantity squared. Here's a linear term. Here's a constant term. Let's integrate this over the entire interval, which goes from x0 to x2, where x2 is x0 plus 2h. And lo and behold, look at that. H over 3 times y0 plus 4y1 plus y2. Same formula as in the book. There's that 4 there. So again, this is confirming something I wouldn't want to do by hand, that when you integrate the quadratic approximating polynomial for 3 nodes, that's what Simpson's rule is doing to give you your approximation. There's where it comes from. It's not showing the error, it's showing the approximation. Okay. If you want to do it by hand, I won't stop you. But okay. But it's nice to see it confirmed this way as well. All right. Have a good day.